So hello again. Tonight we're going to talk about how you would take a radio antenna like you'd use for amateur radio astronomy and mount that on an optical telescope mount. Not with the telescope, but take the telescope off, put the radio antenna on. This is sort of a lead up to I'm taking a telescope mount and it's a manual mount and I'm modifying it to have motors on it so that I can use it as a motorized mount for a radio astronomy antenna. So what's the problem with why do I need this telescope mount thing for my radio antenna? You can see on the right there a picture of a time delay integration or broom sweep antenna. You see it's just sort of manually propped up at a tilted angle. As the Earth rotates, it'll see a different part of the sky. But if you want to see like not just that elevation, you want to see a higher or lower elevation, then you've got to make multiple 24-hour sweeps of different angles, and you've got to go out and tilt it up a little more, tilt it up a little more, tilt it up. And that's how you do your imaging of, hydrogen line of the galaxy disk. Let's say you wanted to see another target. You wanted to see a quasar at a different frequency. Well, now you've got to know where it's going to be and point your antenna in that direction so that you can take, radio imaging of some other target that's maybe outside the Milky Way. You want something that you can at least manually adjust without spending a lot of money on it. So it's not going to be, fully computer automated go-to that you can use with Stellarium, but you should be able to change the azimuth and the elevation or altitude. Now, the next thing is you see this antenna in the picture. It's not weatherproof. It'll become like a rain bucket if it starts raining. So you'd want to set up a rig that would allow you to use it permanently outside. And you're just inside because you know that you can do radio astronomy in the daytime or when it's raining. Wavelength dependent. Some wavelengths are absorbed by water molecules more or less, but there's a certain wavelength range that goes right through the atmosphere, day or night. And so you don't have to wait for it to get dark outside to do radio astronomy. That's another thing is you might want to just leave the antenna outside and put the receiver inside. And that way it's always ready to go. It's always, good to go. And you don't have to set up a bunch of stuff, do your observing, tear it all down because it's not weatherproof. So there's no trouble mounting a radio antenna that could be used for radio astronomy at a fixed position on a pole or a mast or something like that, or a pipe. That just kind of comes standard with you buy a radio antenna, you get brackets with it. There's two kinds of bracketing systems. You can see on the right, there's that kind of L-shaped one that the cord's coming out of. That's the mounting bracket we're going to focus on. And then the two horseshoes used to mount it onto a pole, those are the ones we're going to set aside because we don't need that. But you kind of get those kind of mounting systems. But what we really need to do is to mate that L bracket with something that we can mate with a optical telescope mount. So you're looking at the bridge from one to the other here. Upper right is a manual telescope mount. Lower is the radio antenna. So how do you get one to the other? You see that little upper arm thing in the top image? It's like a bracket that holds things on. And as long as the antenna is light enough in weight and not like a giant swing arm, 7-foot long Yagi style antenna, you should be able to use a small optical telescope mount to mount an antenna and get it to move your antenna. But you need to adapt it. And here's where the adaptation comes in. If you're accustomed to optical telescopes, you'll notice that on the bottom of the telescope, there's a rail. And that rail is called a dovetail plate. And the reason why it's called a dovetail plate is because it's wedge-shaped towards the outer edge of it like a tail of a bird dove. So that's why they call it a dovetail plate. But that's the plate on the telescope. On the telescope mount, there is a dovetail plate receiver. And there are kind of standards for doing this. They're sort of commercial vendor consortium standards, but there's a way of doing this. So you would have a way of taking the antenna and putting one of these dovetail plates on it, and then you would slide that into the dovetail plate receiver on the telescope mount, and then tighten up a bolt that would hold it in place. There's two kind of major brands or styles of dovetail plates. There's what is known as Vixen. Name of the company is Vixen. Their parent company is Cinta. And then there's Losmandy, and a company that makes very similar things is called ADM. So the two styles are Vixen and Losmandy. They're not compatible. The widths are different. And even if you went with kind of Losmandy's Vixen-like, the angle of the dovetail is a little different, but they're reasonably compatible. So as long as you keep the weight low enough of your antenna, you can put it on a regular low-end telescope mount. So here's a close-up of that dovetail plate receiver. And you see the four silver bolts. Those hold the receiver onto this is particularly the elevation or altitude portion of the mount. And you see the red knob, that's the main knob that holds the bar in. And then to keep the bar from sliding back and forth, you see a little silver set screw there. So the cheaper ones won't have that little silver set screw, they'll just have one knob. The most expensive ones don't actually use a knob because that scratches up your dovetail plate. They actually have a little bar, and when you turn the knob, it pushes an aluminum bar into the side of the dovetail plate to hold it in place. That's expensive. How about just a screw? Screw's fine. But it doesn't matter whether you're using an equatorial mount or an altitude azimuth mount. You can have these Vixen style dovetail plate receivers in them. That's what you want to do. You want to mate your radio antenna to a dovetail plate so you can install it onto your telescope mount. And the plates are 1.73 inches or 44 millimeters wide. Take a note, because sometimes they won't make them 1.73, they'll make them 1.75, and they won't quite fit nicely. But the lengths of the plates, you can get different lengths. You can get them 4 inches all the way up to like 18 inches, but you only need really a short and a long, depending upon how big your antenna is. The longer the plate, the more holes it has in it, the more of those holes that are like threads for bolts, or the more screws that come along with it, increases the cost of the plate. But a small plate, about 20 bucks. A longer plate for a bigger antenna, about 50 bucks. But why not use the Losmandy dovetail plate system? It's expensive. It's big and wide, which means it's meant really for heavier telescopes. And we're not running heavier stuff. Doesn't stop you from doing that. So, if you've got a bigger antenna and you want to put a Losmandy plate on the bottom of it and put it on your big telescope mount that has a Losmandy dovetail plate system on it, that's fine. But if you're on the lower end, if you want to keep the cost low, the weight low, go with the Vixen dovetail plate system. And you remember me mentioning that the Losmandy Vixen style is a little bit wider. It's 1 3/4 inches. It's not, it's not 1.73, it's 1.75. So it's a little different. Reasonably compatible though. But another reason why is the Losmandy D series, the wider plates, are expensive. They actually make them 4 inches now, but 3 inches is quite common. But the plate, just the plate itself, an 8-inch long plate would be $120. Compare that with $20. That's $100 more. If you want a longer plate, they're going to be over $200. So the mount's going to be more expensive. The plate's going to be more expensive. Sure, it can carry a heavier load, but you don't really need that for a low-end antenna. So what if you want to leave the mount outdoors? Typically, you're not supposed to leave an astronomy mount outdoors. But there are ones that are made nowadays that if they get rained on and they don't have electronics, no biggie, you just wipe them down, they're fine. All of the exposed metal is covered with heat-treated paints, hard paints on it. Most of the mounting hardware is stainless steel. Very few pieces of it are iron, as older style bolts and nuts and set screws would be. But if the only thing that is iron are the set screws holding the adjustment knobs on, then you can just buy yourself some stainless steel set screws and replace those. You want to make sure that the drive mechanisms aren't cheap metal that might oxidize in the presence of salty water like rain. Want to make sure that they're not destroyable by sunlight like plastic or nylon, that they're a good gauge of brass because they're going to get wet, they're going to get exposed to sunlight. And if anything is covered, you want to make sure you can seal the cover, like that big piece of black plastic. It's really just a well area, and you don't want that filling up with water. So they give you a plastic cover plate that goes there. But I'd take some viscous glue and seal that up because I don't ever need to get in there once I deploy it. And the second reason is the replacement cost. You don't want to spend a lot of money on a mount that you're going to leave outdoors and then have a high wind unexpected or a hurricane come through and destroy your mount. You don't want it to be that expensive. So, you probably already know about when the hurricane came through, it destroyed my antenna. So I had to replace my antenna, which was $100, $200. I could do that. But you don't want to put $1,000 mount outdoors and then I have to either have the weather or unexpected winds tear it apart. So it has to be durable. But increasing the metal mass is not necessarily what it takes to make it sturdy. There's a balance between the size and length and wind loading of the antenna versus the ability of the mount to carry a certain weight. A heavier drive is not necessarily what you need at the low end. So if you take your antenna and you use whatever its mounting bracket is, and you put a Vixen style dovetail plate into that, now the telescope mount doesn't care what kind of antenna you use. So you can start out with a particular inexpensive antenna like that wedge-shaped white one towards the bottom. That's good for listening to a lot of different frequencies, including hydrogen alpha, the hydrogen line, but you need an amplifier behind it. Once you get used to that and you go, I want different kinds of antennas, then you can get that little semi-sliced parabolic dish. It's an open grid dish, so it's not heavy wind loading. You can get that one, but you've got to make sure you put the mount plates on them so that they can be mounted onto the telescope mount. So you need a Vixen dovetail plate, but the Vixen dovetail plate, if it's a smaller one, a $20 one, it's cheap enough and it's easy enough to mount them. You do need a drill because the holes aren't in the right place. That you can, maybe have 2 or 3 kinds of antennas if you get serious into radio astronomy, because different things need different antennas, and you can just swap them out, unbolt it, pull it out, disconnect the radio cable, connect the radio cable, put it back in, you're good to go again. But if you're going to put a dish up there, you need to make sure that the dish antenna is an open grid, not a solid full-size parabolic antenna. There's a popular one out there in the do-it-yourselfer market called a Kraken Discovery, that it's a small dish and it's solid and it's made out of metallic infused plastic. But if it catches a high wind, it's going to be a sail and put a lot of stress on your mount system. So probably not the best one for you to do that with. And when you connect it up, you want to make sure that the radio frequency cable mates nicely to your software-defined radio receiver, and that the impedance of the cable is 50 ohm, not TV style, which is 75 ohm. And the antenna can be outdoors, the mount can be outdoors, the cabling can obviously be outdoors, and then everything indoors is comfortable inside. And this, I keep showing you this picture, this particular manual mount that I'm going to be putting motors on. Another aspect of it is, you see how the upper drive is kind of on a bent arm? That allows the antenna, if it's got a long boom on the back, to be tilted vertical, 90 degrees. If it was directly over the top of the other axis, it would bump into the mount. It would bump into whatever's below the mount. But by being canted backwards like that, you can go fully vertical with it. Some altitude azimuth mounts, like the Celestron heavy-duty manual mount, they're not full range. They're limited range. And you have to unlock, manually move them to another part of the sky, lock them back, and then you're good to move maybe plus or minus 10 degrees. And then when you want to move to another part of the sky, or as the Earth turns, things move lower in the sky, you've got to go out and unlock it, move it down further, coarse positioning, and then lock it back and do your fine positioning. This particular mount will do 360 around azimuth and will do 0 to 90 in altitude or elevation. So It gives you full range of motion without having to go outside and unlock and reposition. Okay, this is a lot of text, but I'll show you the text for a few seconds so you can like snapshot that if you want to. I'll show you on the next page the breakdown. Okay, so you've got the antenna. It's got this little tiny L-shaped or flat bracket on it, and you've got to mount that to your dovetail plate. But how do you get it counterbalanced? You take a heavy-duty L bracket like you'd buy at Home Depot. You drill a couple of holes through the mounting plate, and you put some bolts through it, and then you drill a hole through the other part of the L bracket, and you get a threaded rod, and then you buy a 2.5-pound weight that's intended to be used on lightweight telescopes, and you can rotate the weight on the threaded rod, and now you have a way of dynamically adjusting the front and the rear loading of the counterweight. So you can mount the plate onto the antenna, mount the L bracket, the threaded rod, the weight, and you can use lock nuts and fender washers to hold the weight in place once you get it balanced. And then you can put that on your telescope mount, and now you can balance the weight of the antenna versus the weight of the counterweight, and it puts less strain on your mount. But since this is a lot of weight, you want to move the weight slightly towards the counterweight. And the reason for that is so it puts constant pressure on the gearing system. There's not like perfect balance, and as it moves past like middle, it kind of like quonk quonk, it goes through a lot of backlash. You want to always have pressure towards the back end so that the gears always have pressure against them so you don't have any backlash, or it reduces the backlash. The total amount of weight, the antenna plus the dovetail plate plus the L bracket plus the threaded rod plus the counterweight plus the nuts and the washers, that total weight needs to be roughly 50% of the total carry weight of the mount. Which, well, what is that? Well, what it amounts to is if the weight's 2.5 pounds, that's 2.5 out of your 5 or so pounds total weight. So the counterweight and the antenna are pretty much close to 5 pounds. So you've got maybe a pound or two left, and the Vixen dovetail plate is made out of aluminum. So that's fairly lightweight, but the threaded rod is stainless steel and the L bracket is heavy metal. So yeah, there's a balancing act you have to do to make sure that you stay within the total carry weight. Now, why 50%? You can go above 50%, but it puts more strain on the mount. This is the normal course for even optical telescopes. They'll tell you when you buy your mount, find out what the weight is of not just your telescope, all the stuff you're going to put on the telescope, the diagonal, the eyepiece, any solar filters, any cameras, any finders, weigh that whole thing, and then that should be roughly 50% of the carry weight of whatever the mount is you buy. So the formula works the same. It's just different pieces. Optical telescopes have a very narrow field of view, FOV. They're going to be looking at a degree or less of field of view. A radio telescope is a little more forgiving. It may have a couple of degrees field of view. So if it wiggle, and you're also working with much lower frequency, much shorter wavelengths than you would with optical. So it's more forgiving. You can have a slight amount of wiggle, and you can like position it and then wait for the wiggle to die down a little bit before you start receiving. The amount of slop, wiggle, backlash is far more tolerable for a low-end mount with a radio astronomy than it is for an optical mount for taking pictures. I would still advise, if you've got a large antenna, try avoiding using it in other than a calm wind, if there's any wind. If you see that your antenna is wiggling, undo the Vixen, take your antenna loose. But that's just how to maintain it long term. If you know the wind is coming, if there's a tropical storm warning or a hurricane, it's easy enough to remove it. And as they say, proof is in the pudding. So here's 2 proofs. At the top, there's a small Yagi antenna, and at the bottom, there's a much longer Yagi antenna. These are different wavelength antennas, different amplitude, but the bar at the top, the black part, the black bar, you can see that's shorter. The green bar at the bottom is longer. It's because there's a longer antenna and I wanted to get the counterweight further back. But the L bracket is similar. That silver thing that's sitting on top of the Vixen plate, that's the L bracket. And the reason why you want the counterweight on an L bracket is you have to think of the counterweight as not only do I have to counter the weight in one dimension, I have to counter the weight in another dimension. So putting the counterweight above the center line of the antenna a little bit with the plate and the antenna plate towards the bottom counterweights vertically, like the screw adjustment weight will counterweight horizontally. So that's why you want an L bracket. And does it work with other kinds of antennas? Well, yes, indeed it does. Here is my hydrogen line parabolic antenna mounted on a 13-inch long, black, in this case, Vixen dovetail plate with an L bracket and a 2.5-pound weight. A 2.5-pound weight should be plenty because you can adjust the leverage it has by moving it up and down the threaded rod. Remember, keep the total weight down and offset it slightly to the rear. But it is inappropriate for some kinds of antennas. This is an omnidirectional wideband antenna. You might see this like at a ham radio enthusiast's house, an amateur radio. These are very good for pointing straight up, and they're very good even in moderate wind because they'll just wiggle, they'll whip around, no problem. But if you took this thing and you put it on a plate and you wanted to tilt it, the moment that you brought it down below 90 degrees, that top portion would just droop. And the moment you said, okay, it's drooping down, but I've waited until it stopped drooping, and now I'll turn it to the left a little. And as you did that, it would whip back and forth, kind of like they call it whip antenna. So there are some kinds of antennas that the Vixen plate on a radio telescope, on an amateur astronomy telescope, are just not appropriate. So what kinds of antennas do I need for what frequencies? Well, it depends upon your targets. If your target is Jupiter, you want to listen to radio Jove kinds of things, then the frequency range you need is 18 to 28 megahertz or megacycles per second. If you want to listen to ionospheric disturbances from like solar wind and such, that's 20 to 40 megahertz. If you want to listen to meteors hitting the ionosphere, that's 50 to 148 megahertz. If you want to listen to solar prominences while you're pointing at the sun, that's 20 to 300 megahertz. And if you want to listen to the hydrogen line, that's 1.4 gigahertz or 1400 megahertz. What kind of antenna? Well, there's all kinds of antennas to listen to different things, different frequency ranges. You may find one that has a wide frequency range, so it's good for a lot of targets, but at the same time, it doesn't amplify a lot. So different antennas for different crowds, and some antennas need a low noise amplifier or an LNA. Cables and connectors. Avoid a TV antenna because it's going to be 75 ohm and you need a matching transformer to get to the 50 ohm of your software-defined radio receiver. Also, radio antenna, TV antennas have an F-type connector. You need an SMA connector. Don't wrap it around your house kind of thing with the antenna cable. Get it close to wherever your software-defined radio is. If a 25-foot cable works, go with a 25-foot cable. Don't go, what's a bargain? I can get 100 feet. No, you're diminishing your signal. Get a cable that has a good metal braid in it and that has a good thick polymer sheath. So you have good resistance from noise on the line, and you have good resistance from outside noise entering the line. There are two kinds of SMA connectors. The one that's here in the picture is called an SMA male connector, and you can see it's got a little pin sticking out in the center. There is something called an RP SMA. That stands for reverse polarity SMA, and it'll still be a male, but instead of having a pin in the center, it'll have a recess, a tube into which a pin from the other side connector goes in. So don't expect to use a Wi-Fi antenna for your software-defined radio antenna because it'll have an RP SMA, and now you've got to have an adapter. Well, there's nothing wrong with adapters. You can physically get them to mate. They sell those on Amazon. But if you don't need an adapter because you bought the right kind of antenna, and then that's better. If you're using like a regular amateur radio or ham antenna, those will either have an N-type connector or a PL-type connector. and you'll need an adapter to get to SMA. They now actually make antennas that you can buy at a reasonable price that come with the male SMA connector on the end of them. You don't have to have an adapter. So when you buy your extension cable, you want to buy it with a female SMA to a male SMA. That is, you can connect it directly to the antenna with the female, and then you can connect the male directly to your software-defined radio receiver. And it's convenient because if you want to do like indoor testing or like no cable needed point-to-point testing, you just take the cable out of the loop, plug the antenna directly into your software-defined radio, and you're good to go. If you pick like male to male or female to female, now you've got to have an adapter. And if you didn't know it or not, the amateur radio ham antennas, PL is plug, but you've got two versions. You've got a 239 and a 259. And in the case of SMA, they call it male and female. In the case of the amateur radio antennas, there's a PL 239 and PL 259. One is the male, one is the female. So you may get confused by the 239, 259, but that difference is just male versus female. So in summary, amateur radio astronomy is something you can do with a manually positioned antenna and expensive. You can let the Earth rotate underneath the target and you'll gather data that way. It's an inexpensive starting point. But once you outgrow that, you want more. You want it to be easier. Then you probably want some kind of mount that you can manually adjust things with knobs. And if you take that to the next level, you want something that you can maybe drive with a motor. Maybe not fancy, maybe not computer stellarium go-to, because that's going to be expensive, but at least something you can go this way, go that way, different motor. And that's the one I'm focusing on now, is just, can I move the antenna with a motor control system not connected up to a computer or stellarium? And that's taking some time to get it right. But it makes more sense to use a Vixen style dovetail plate system than a Losmandy D series, because that would make the plate more expensive, the mount more expensive, and you can carry a lightweight antenna easily. If you want to make a big antenna move or a solid dish antenna, you're going to need something bigger and more expensive. And since the wider field of view of RF antennas is different than optical, then you can use an antenna mount system that has a little bit of wiggle and be tolerable with that. But if you have a more unconstrained budget, go for it. This is just a concept. But remember, if you want to leave it outdoors, so it's always at the ready, you want to get a mount system and an antenna that you can leave outdoors and understand the total cost of ownership of the whole thing. I plan on having a presentation in the future about a motorized system, and I'm still working on that. And then I can match it with the links. Broom scanner. And then what's the difference between a Vixen and a Losmandy dovetail? And what are these antennas, the Yagi things that I speak of? They're actually Yagi Udas, but you can see there's three different antennas there. One is 700 to 2700 megahertz, which, hey, that covers 1.4 gigahertz. That'll do hydrogen line, but it's only 10.6 dBi. And that's the sweet spot. That's right in the middle. So you won't get 10 dBi at hydrogen line. You'll get more like 8 dBi, which is non-trivial, but if you look at the bottom one, the parabolic antenna, it's specifically designed for hydrogen line at 1.4 gigahertz, and it'll give you 20 dBi. And the way the dBi scale works is every time you go up by 1, you're going up by 10 on the amplitude. So much better. And then, if you said, well, what would be a average dovetail plate length? I've got an 11.8 inch there that I've used. The counterweight system, the screw thread with the 2.5 pound weight, the threaded shaft, and then how you would mount it. You still have to use a drill, but stainless steel nuts, fender washers, split washers for locking it in place. And then that L bracket, a lightweight shelf bracket that's thin metal would likely bend under the weight of the counterweight. So you need one that's fairly thick metal that's outdoor durable. So a galvanized one that you can use outdoors. And then what would be this manual mount thing? There's the mount that I show in the pictures, and I'm adapting it for motor control in altitude and azimuth. Comments, questions?
Yeah, one time I made a jib arm for a camera,
Yeah,
and I had the same problems you have.
counterweight
Uh, Counterweights, right? So
and
I was
wiggle.
able. Well, I wound up with these ladies' hand weights that they use for
Yes,
exercises. Very cheap,
yeah.
and you can drill them. You can put wires around them and all that.
Mhm.
It's adjusted left and right, things like that.
Yep. Well, I wanted something I could leave outside, and I wanted something that once I got the weight just right, I could take the nuts on each side of the weight on the threaded shaft and tighten
Yeah,
them down, and maybe even put some Loctite on them or something, and then it's
yeah,
good to go.
yeah.
But I just found that the Losmandy weight system works great. I don't like their bar. I don't like their wide dovetail plate because that doesn't fit on my cheap mount. But the plate system, no. The counterweight system, yeah, I just take the threaded rod out of it. And the threaded rod actually has a bolt hole in the bottom of it because it's meant to go on a slide rail. You take the bolt out, don't need the slide rail. In fact, I'd like to buy it without the slide rail because it might be a little cheaper. But I think it's about $50 and you get the threaded rod, the bolt, a washer, and the threaded weight. So that's something that's doable.
Weight is good because it's good
Yeah,
for
Helen has actually used vinyl bags full of sand or water, and
Yeah,
you slide them out the length of your boom, but your boom has to be fairly long because you're not really carrying that much weight. She uses it on the parallelogram for binocular, but yeah, you have to think about all that counterweight stuff. Um,
yeah. Weight times distance. Yeah,
yeah, if it's that little sort of white arrowhead antenna, that sucker is light enough weight. You can slap a plate on the bottom of it, and as long as you pull it really close to the telescope, you don't need a counterweight. The problem is the telescope mount head, if you've got a computerized one, it's got motors that are making magnetic RF fields, which can affect your radio reception. So yeah, you need the Vixen plate to like get the antenna further away from the mount, and that requires you to have more counterweight on the back.
never thought of that. Noise from the motors. Yeah,
Yes, but they're magnetic fields, and you're doing radio.
yeah, yeah.
Also, when the motors run, if you don't have capacitors on the motor power lines, they can produce noise in RF. Um,
Right. Yeah.
so yeah, you have to think about all those things. I have obviously. So I people can say, well, I can do it cheaper doing this. Like, yes, you can. Yes, you can. Can you leave that outside in the rain? No. Okay, then that's why this is different. Or I've got a 4 foot long Yagi that I do wideband cross pole. Like, great, you're going to need a longer Vixen plate. Still only a 2.5 on the back. But when you go to move that sucker and you stop, it's going to wiggle for a little while. You just have to wait for it to damp down. As usual, minutia, but that's what I'm into is oh, that's a problem, fix that. Oh, that's a problem, fix that. And when you get done, it's like, I spent $500 on all this? Well, the mount only cost $140. The counterweight system, $70, including the Vixen plate. Okay. So yeah, it adds up. But if you want to start at the low end, you can start at the low end and then work your way up as you need it. But you won't get to $1,000 is the best way to describe it. You might get to several hundred, but you're not going to get to 1,000.
Yeah, at Home Depot, I used to buy these drawer sliders and
Yeah.
use them for all kinds of things. Yeah,
Oh yeah. Repurposing things. That's what you got to do.
yeah.
Like I'm repurposing a radio antenna for radio astronomy, and I'm repurposing an outdoor shelf bracket as my weight bracket, and I'm repurposing the weight system meant for a telescope
She's on.
to actually counterweight an antenna. That was something my father taught me a long time ago. Just because you bought that screwdriver as a screwdriver doesn't mean it can't be used as a hammer.
My boss at the phone company says, "What are you climbing up that pole with your whole tool belt? Just take a Phillips head screwdriver up there. You can use it for all kinds of things.
Yeah.
Use it for a hammer, use it for a drill.
Yeah. Take a hammer and take no, don't even take a Phillips head. take a narrow slot head, because the slot head can be used on a slot head or it can be used on a Phillips if it's narrow enough.
Yeah.
Oh,
You can make holes with it. You can do all kinds of
oh
stuff.
yeah, you can punch things.
Yeah.
If an eagle attacks you, you can ward off the eagle.
Squirrels is the problem.
Squirrels, yeah. Any other comments or questions before I stop recording? Hearing nothing.